Okay, so for this next lesson, we've looked at already kind of what the electric force looks like. We said it was similar to gravity in a lot of respects, which is true. And the electric field actually is very similar to the gravitational field in a lot of respects as well. These two forces, or these two concepts, are very kind of closely tied together. And we've already seen, like, if we've got masses like this, I'm not going to do these full examples. We've already looked at this already. Well, I'll fill in these ones down here at the bottom, but we've already seen for objects that have mass, they have a gravitational field around them, and so their gravitational field is pulling in all directions. This thing has a gravitational field pulling in toward it. And the gravitational field is given to, the gravitational field is given to us by, I'm just going to go down here, little g, where little g is big G, the universal gravitational constant, times the mass divided by radius squared. And that came from F, the force of gravity, being equal to gmm over r squared. The gravitational field is just this part, the gmr squared part for the massive object m. If we look at the electric field now, we've seen a lot of really analogous things. The force of electricity was given to us as kq q over r squared. And so and if we think back to the gravitational field, we said, okay, it was the gravitational field strength times a mass acting in that area. We had Fg equals gm over r squared, and then we had another m. This piece here became g, gravitational field strength, so analogously, this piece here is going to become electric field strength. E equals kq over r squared. And depending on the charge, whether it be positive or negative, like with gravity, the gravitational field always went in towards the object. Depending on the charge now, these electric fields are going to look different. So I'm just going to put this formula here as well. So we've got the electric field is equal to kq over r squared. And if we look at it as defined as a ratio, we can say that the Fe equals q times E. Oh, sorry, that's below where it should be. Because as we've seen here, we saw that Fe is kqq over r squared. So we can talk about the electric force now as being equal to q times E, or we can rewrite this and say, well, my electric field is equal to the electric force divided by the charge that's in it, the test charge that's there. The units for, if we take a look at what these units are, electric force is measured in newtons, charge is measured in coulombs, so the units of electric field are newtons per coulomb. So very similar in a lot of respects to gravity. The only difference here now is that this thing can go either into an object or out of an object depending on its charge. Let's take a look at another example here. At a certain point in space, we have a negative 0.5 microcoulomb test charge experiencing a force of 5.2 times 10 to the 4 newtons towards the south. We want to find the electric field strength at that point, and we want to find the electric field strength 0.45 meters right of another charge. So A and B here are totally disconnected from each other. So let's look at A first. We've got, all we're told is that somewhere, I'll put it right here, we have a test charge, which I'm going to call Q, and we can label Q as having a charge of negative 0.5 times 10 to the negative 6 coulombs. We're also told that this thing is experiencing a force downwards. And we're told that that force is equal to 5.2 times 10 to the negative 4 newtons. So the question then becomes, what is causing this? Well, if we've got a negative charge having a force downwards, one of two things is true. Either we've got something big and positive down here, or we've got something large and with a large negative charge up top. We don't know. Either way, this thing is experiencing a force to the south, so there has to be an electric field present here. So we can figure out what that is, and we can use the second of the two relationships that we had. Say, well, Fe is equal to Q times E. We know the electric field strength. We know the electric force, or the strength of the electric force, is 5.2 times 10 to the negative 4. And that's going to be equal to 0.5 times 10 to the negative 6. Remember, in our force calculations, we don't use positive and negative. The positive negative just gives us the direction. And then we want to multiply that by E. So we can run this thing through and say, okay, well, divide that over. We're going to get an electric field strength of 5.2 times 10 to the negative 4 divided by 0.5 times 10 to the negative 6, and that's going to be equal to 1,040 newtons per coulomb. And so the electric field strength at that point is 1,040 newtons per coulomb, and this charge is experiencing a force as a result of that. Relatively straightforward. Part B is find the electric field strength outside of a charge, and so let's do B. Basically, these two examples are just showing you the two different ways we can find electric field. So we've got a charged object that has a charge of 2.3 times 10 to the negative 6 coulombs. We're told that it's positive. And we want to know over here in space, this distance is 0.45 meters. What is the electric field at that point? Well, for the previous one, we could use this relationship, Fe equals QE, where Q is the test charge interacting with a field. So we had the force on the charge and we had the charge itself. In this one, we can't do it that way. This thing's not experiencing a force, so we can't use this expression, so what we're going to have to use is our other expression. We had the electric field from a charge is equal to KQ over R squared. So K is a universal constant that we've got on our formula sheet, 9 times 10 to the 9. Q is the charge on the object creating the electric field. So in this case, that's going to be 2.3 times 10 to the negative 6. And the distance from that charge is 0.45 meters, and so that becomes our R in this formula. So then we get an electric field strength, if we run that math, of 102,222 newtons per coulomb. So it doesn't take much of a charge to give us a fairly substantial electric field. So that's it. These are two different ways to calculate it depending on what the information you're given. If you've got a charge interacting with a field, we can use the force to give us the strength, or if you've just got a charge sitting in space, we can find out what the electric field due to that charge is. That's it. To give direction for an electric field, we use what's called we use test charges to see what would happen. So the direction of the gravitational or the electric field With gravity, this was never an issue since gravity always attracts. Since electricity can attract or repel, we need a definition. We say that the direction of an electric field is the direction a small positive, so a small imaginary positive test charge would go if placed at that point. So, for example, I'm just going to jump, well, we can talk about all these. If we had a negative test charge and a force downwards, what does that imply? That implies that we've got either something large and positive here with field lines, or we've got something big and negative up here with field lines. Electric lines drawn to determine electric field. These look terrible. So the question is, if this thing is experiencing a force downwards, if we put an imaginary positive test charge here. So let's imagine that we've tossed a positive test charge here. Which way would this thing go if it were to experience either one of these things? This thing would go that way. The positive would be attracted to the negative, or it would also be repelled by this positive, so it would be going this way as well. So what that means is, for a negative test charge to be experiencing a force downwards, this thing, the electric field in this particular problem, has to be going this way. So same thing here. I've got my test charge. It's positive in this case. So these are the last two examples we just did. At this point here, let's say I put an imaginary positive test charge. What's going to happen to this thing at this point due to that? Well, these are both positive. It's going to be repelled. And so this thing is going to have an electric field going to the right. So we can put this kind of all together. If we put a positive test charge around a actual positive charge, it would be repelled in kind of every direction. And so what we can do is we can see that for a positive test charge, or for a positive charge, the electric field is always out. And it's got to be the opposite, right? If I put a positive test charge here, it's going to be attracted to that big negative. That means the electric field has to be going into, by our definition, negative objects. So direction of electric field, out of positive charge into a negative charge. So we'll do a couple more examples here. We want to determine the electric field of two charges. The principle of superposition states that we need to find the vector sum of the field of the individual charges. This is the exact same thing we did with gravity. We said, okay, if I've got the moon here and or the earth here and the moon here, what is the gravitational field strength in the middle somewhere? And so we found the strength of each field and added them together. We're going to have to, based on their directions. So one would have been positive, one would have been negative. We have to do the same thing here. So if we take a look at what we've got here, I'm going to color this guy in red just to be clear what's going on here, and this guy's going to be green. So at this field point, the red charge is going to have an electric field going to the right, and the green guy, because he's also positive, electric fields go out of positives, he's going to have an electric field going that way. And so we have to figure out what these two are. We've got to add them together appropriately. At this point, I think it's proper to determine what direction we want to call positive and what direction we want to call negative. Let's call it that way. A positive direction. Let's figure this out. To figure out what the electric field is from this guy, we're going to use this formula. The electric field is equal to KQ over R squared We fill this guy in, we're going to get 9 times 10, or 9 times 10 to the 9. It's 1 microcoulomb, so 1 times 10 to the negative 6. And the distance is 1 meter. So it's going to be 1 squared. And we're going to find that the electric field due to the red positive charge is equal to 9,000 newtons per coulomb. And it needs a direction to the right. So for this green guy, the equation is exactly the same. What does the electric field do to a charged object? Well, it's kq over r squared. So this is 9 times 10 to the 9, 1 times 10 to the negative 6. And now if this distance is 4 and this distance is 1, this distance has to be 3, I'm hearing everybody say. So the electric field strength here is 1,000 newtons per coulomb to the left, which means that the net electric field, we said to the right was positive, so the net electric field is going to be 9,000 newtons per coulomb minus 1,000 newtons per coulomb, which is going to give us a net electric field of 8,000 newtons per coulomb. We can use kind of this particular example to do the next one. We can see here, in this case, we're not asked to find the electric field strength everywhere, but we're going to just kind of draw it in general. So if we take a look at what's going on here, I've got 2 equal 1 microcoulomb electric charges, and we want to see what the electric field is kind of between them at all points. So here, closer to, if we look back, closer to the red one, the one on the left, we had a, oh, and I didn't put it in here, and I should have, 8,000 newtons per coulomb to the right. So the net electric field was to the right, because we were closer to this guy, even though, and these two charges were equal. So we're going to have an electric field going to the right there, but that means here it's going to be going to the left. Smack dab in the middle, what has to be true? Well, smack dab in the middle, electric field has to be 0. Because at this point, we're the same distance away, and we're heading in exactly opposite directions. But what about this guy here? Here, we've got a positive charge, so it's going to have an electric field going this way. This guy's going to have an electric field going this way. They're going to be equally strong, and so when we add these things together, I move this guy tip to tail, and so we can see at this point, we're going to have an electric field going up, which means if I had the same point down here, I'd have an electric field going down. We have to add them up using vectors. So like with this guy here, at this point, you'd have a large upwards here, but you'd have a small to the left coming from that way. And so this guy would be kind of off to the left that way. And so what does that actually look like if we draw everything in? Flip the page and let's do it. So for 2 positive test charges, what we have is something that looks like this. It'll go straight to the left over there, and it'll go straight to the right over here. In the middle, there is nothing. But we do know that it starts going towards the middle from either side, but as it approaches the middle, it's going to cancel out. So what's actually happening here? If we visualize the electric field, and there's all sorts of great YouTube videos that do this, we can see here that the electric fields start to push on each other, and they also almost look asymptotic. You're really close together without touching. So the same thing with these guys. So what you're going to get is you're going to get something that looks like this. At some point it'll go straight up, but it'll start to curve. So for two positive charges, the electric field is going to look like this. Where they kind of push up against each other, and right in the middle, there is no electric field. If you have a positive and negative, this is really easy. It's going to go out of the positive into the negative. So this one's always going to the right. Out of him into him. And so even for all these guys going out, they're going to be attracted into that negative. You're going to get something that looks like that. Constantly, the electric field lines go out of the positive into the negative. The only place where they don't loop around is straight out the left-hand side. There would be no up or downwards force or component rather from this guy to pull them back in. So, as a bit of a summary, we can see that the electric field, it can be found using the force on a test charge. And to find that, we said the electric field is equal to the force divided by Q. Q being the test charge. We also said that the electric field can be found outside of a charged object using this formula. E equals KQ over R squared. And if we go back, and we're just going to start collecting results here as we go, the force on a charge can be found using, if we remember, F equals KQQ over R squared if it's between two charges, or we can now find the force on a charged object in an electric field using F equals QE, where Q is the charge on that test charge and E is the electric field strength in that area. So I want you guys you're going to practice some stuff here for me. Again, this stuff is very similar to gravity. Hopefully it's clicking for you. I want you to take a look at I want you to do number 1. I want you to do number 6. I want you to do 8. I definitely want you to do 10. 10's a great problem. I want you to do 11. And I want you to do 15 and 16. Any comments, questions, concerns, please feel free to let me know. Otherwise, good luck.